is how it works. Um, Nothing much to explain here, but at a broader level, if you guys are comfortable, then typically in a tetrahedron, at each of these nodes, you have 3 degrees of freedom. Is a shell element, they have 6 degrees of freedom, and in a beam element at the nodes will have 6 degrees of freedom. So it finds when the degree of freedom at each node is increasing, we are actually presenting more dimensions of the actual model and makes it more accurate. But on the other hand, we are also optimizing on the geometry. So its own pros and cons, we need to use it appropriately. Nodes and elements. Next one, I am moving on to directly into stresses or the kind of outputs we are getting from this software. Now, I first by default blindly also or without much thinking, we are seeing only one result, which is called one mesh stress. Am I right? We end up thinking of only this stress, and of course we do have stresses which are equally important, like principal stresses, shear stresses, etc. And if you take this example, say this Q, if this particular Q, and if I have applied the force, say in this particular X direction, they're being called as planar stresses. So assuming this force is in the X direction, this divided by the cross section in this plane gives us stress in the X direction, right? This is of it. Then we have stresses in the Y direction, in the Z direction. So these are nothing but planar stresses in Y and Z direction. Now in the actual geometry, even the force is applied somewhere in the geometry, when it is localized into that element, typically is further divided into X, Y, Z direction applied on that particular element. From when the post processing after analysis is done and the strains are seen, basically we get the strains in the X, Y, Z direction. Those are added into the X, Y, Z stresses in the planar direction. That is X, SY, and SZ. Secondly, when a force is applied in the X direction, say take this example again. If I exaggerate this a little bit more, if this is to be broken, there will be certain amount of stresses which are coming in here, called as shear stresses. So the cross section, which is again, if I say the force is applied in the X direction, and here the cross section would be this plane. That force by this plane, I am getting the shear force in the YX plane. And it's a bit sorry, it's which is plane YZ, XZ. Where is XZ here? Okay, it is represented is a little bit different on this image, but basic idea remains the same. The section over here, which actually parallel to the application of force by this cross section, will give us shear stress in this plane. On the other hand, the force divided by this perpendicular plane will give us normal stresses. Needs to be understood. So we have stresses which are represented in this equation. It is basically the difference and the squaring of it. There also a representation of the shear forces. Again, they are squared and there is certain equation, etc. And complex equation, but it is actually a simple equation which is actually representing all these things and giving us a quantity called as one mesh stress. And for practical purposes, if it is a ductile material, then users accept the stress which is representing on normal and shear stress as stress which can be compared with the yield strength of the material to decide if the part is going to fail or not fail. This is the basic ingredients of a von Mises stress, and the reason why it is used exhaustively, and it has own place because representation for most of the geometries we end up using this particular stress. Then on von Mises stress, while question coming up, let me check what it is. Do we have limitation on the number of elements? Frankly, no. Again, this come up many times. We say no. Like obviously, it is driven from the number of elements that your machine can handle. We have charts which will tell you at how many elements we how many how amount of RAM or what kind of machine. But remember, or frank, outspoken or not. Okay, it is more okay. It is more of a reality for any finite element analysis software. And typically, you understand, this is mathematics. And when we are creating elements, we are actually approximating the geometry. Plus, these matrices are going into a particular solver, and it is basically a matrix which is getting solved. So when the number of elements goes increasing, like from a mathematics perspective, we are actually reducing the accuracy. The accuracy goes lower and lower and lower. So, and I'm talking about millions here. It is not about thousands. When it's about probably 2 million degrees of freedom and more than that, there is a chance of this getting worse and worse and worse. This is a funny thing, difficult to explain in this presentation online, but this is the reality for FEA. So there can be models with 20 elements as well, but it comes with its own cons of losing on the numerical accuracy. It is compensated by different methods, but also a ground reality that when we increase the number of elements, the accuracy can drop down. That needs to be understood. And say we also have 3 different solvers. If you remember, one of them is called as direct sparse, second is FFE, and third one is plus the other two which we have, which is large problem direct sparse, and the new one, the Intel solver. But basically, if I concentrate on only the first two, one of them is FFE, which is called the iterative solver, and then one is a direct sparse solver, which is called the frontal solver. The frontal solver typically is good for low number of elements, that is up to 2 million elements, and it is supposed to give very accurate, crisp result for that. Anything above that, we need to move to the FFE solver, where it is using a iterative process to get the final result. Obviously, it is for high number of elements, it is supposed to be more robust and handle it in a better way. But actually, direct sparse solver is far more accurate than FFE solver. So again, our models, there is no point in covering this solver. The models where we need to go in for certain solver, and depending on that, we stick to that particular solver. It goes on in that way. So it is about elements. One Mises stress. We'll quickly discuss the other two, but before that, any questions on whatever I have discussed as of now? I'm a bit more heavy and things more intricate now. What is the Intel solver and a frontal solver? In due course, we are going to discuss solvers in more detail. So I will I'll come up over there. But to put it simply, is nothing but direct sparse solver. The way it solves is like if you have any SEM book, you should be able to explain it. It is a simple, straightforward matrix where it is just inversing the force stiff known from the geometry and it will extract the strains. In case of Intel solver, I would say it is more of a solver which is more optimized for machines which are using in processor. So if machine has an Intel processor, it is supposed to be more faster and better on those machines. So again, it is a kind of frontal solver and more of speed. If you can experience a faster behavior on those machines. You have exhaustive content on all these solvers. When it comes in the slides, I'll definitely discuss on that topic. If you see here is particular thing called as principal stresses. Typically, now I believe you are all comfortable with what you saw here. If not, please ask. And when I think of this bottom square, you can see that the same element or node or the cube seen for calculating the stresses can be twisted or rotated a little bit. It can be in such a way that when we can reach a state wherein the shear stress, that is these stresses, can go to zero. So I'm sorry, I messed up over there. So the normal stress is specified in a specific coordinate system for which shear stresses are zero. So I'm right. What I said was right. So shear stresses become zero when we rotate this cube in a certain direction such that the load is absolutely perpendicular to the surface on is applied. And when this happens, that we see are called as principal stresses, P1 to P3. So that basically normal stresses, that is X, Y, Z, at a condition where the shear stresses are zero, and that gives a different perspective. There are few other stresses which we are not discussing in detail, but if you have any questions, please ask. We typically discuss something called as factor of safety. So you have understood principal stresses, von Mises stresses, etc. So there's one particular stress which we get from the software, and we also have limit stress, or the stress at which the part can break or will break. So we divide that particular stress by the that is coming in the geometry that will tell us the factor of safety or the buffer that is present in this part to withstand the load. And that should explain what is factor of safety. So typically, instead of using thinking of the stress values, people discuss more of factor of safety that quickly tell them how much safe their part is. And, if I talk in terms of megapascals, it does not make sense most of the time. Instead, if I say the factor of safety is 1, 2, or 3, that tells how safe this design is. That makes more simple. And as of now, guys, I'll give 10 so that you can think forces, etc. Okay, questions. Let's move on. Now, what over here? There is assumption which is happening and which we need to understand. It is called as, especially when we say something called as a static analysis or a linear static analysis. The domains are happening in a linear way. The model behaves in a linear way. If I apply a force of 10 Newton, I get displacement of 2 meters. If I apply a 20 Newton, I can expect a displacement of millimeters. It is simple as that. The loads and displacements are that is a huge kind of assumption that is happening here. Typically, we are also looking at scenarios wherein we are saying this in the software will never break. So it can any amount of displacements and stresses. It does not matter. Stresses. Of course, the displacements are huge. It pops up a warning. But as in terms of displacement, it can withstand any amount of displacement. Sorry, stresses. The first point, which is the response is proportional to the applied load, is well understood. If the load, deformation also gets double. If you remove the load, model has no deformation. And material, this holds good. This is into picture obviously because of material, wherein we are specifying the modulus, which will represent how much amount of stress will come into picture when a strain is applied. It will represent a linear variation of displacement. Like, of course, this is reality, kind of unreality, or if at all it is happening within a range, this can happen. We are assuming that after we remove this load, this will come back to its original geometrical structure and the force is removed. So it depends to its original shape if loads are removed. No deformation happens. Finally, loads are static. Now this is a nice word. As what I said is more towards the linear. The second, static. That is, all loads are applied in a gradual way or in a infinite, or they applied in infinite time. The of time is not considered. There is no if time that is coming into picture. The load is always applied steadily and slowly. This topic of static analysis, that no types being considered, or any questions on linear part of it. Questions? Let's move on. We have understood the process and few basics of simulation. So before you start the analysis, as I told you, the pre-processing part of it, we do a few different things. Like, we need to understand what material has to be used, ensure of it before the analysis. Physical working conditions. Now these could be the forces that are being applied, or temperatures, or any other thing. We need to have a good understanding in detail of these three things. So now you understand the elements of that. Now these forces could be pressures, or welded or welded loads. All those understand. Models, that is CAD part of it, the actual model representation, and if necessary, certain amount of optimization. Finally, once that is done, we are going to create the finite element meshed model, that is FM model of this particular geometry. Shows here. Finally, results are out. We need to understand which results we need to see. so that, or one area under which we are going to accept these results, reject them. We are to decide if the part is going to fail or it is going to succeed. So all things need to be decided beforehand before we jump into the analysis. So on this can be said as a checklist for simulation. So this we will go into the lesson. While I do that, any questions as of for internal purpose or internal evaluation only? We do have the PD, the training manual. As I mentioned, the 2015 is out. Is for yourself. Even I ordered a few for you guys. If anyone wants, please I can share a few training manuals with you guys. Either I meet you personally, or those in Singapore, if you can catch up with me, then I can give you the training manuals that you want. Okay, let's see things here. Quick training manual. The things were okay. So I will be comfortable with these things, building the mathematical model. When we are doing defeaturing or idealizing the geometry, the cleanup activity has to be done. Use this process model FEA. That discussed a few of them, but yeah, that's it. Certain errors can remain. We discussed a draft quality element and high quality element, the one which has the mid-side node and one which does not. Element is also called as first solid element. Okay. With elements, even over there we have first order and second order elements. We discussed a few of those topics. Okay. Choosing between solids and shell. I hope you understood. Any questions, please ask. Is high, solid and shells. Degree freedom, calculus and FEA, interpretation of FEA results. This is very important. Please, you have understood this topic of one mass stress, shear stresses, planar stresses very well. This is the backbone of your analysis. By the if shear stresses become zero, typically the Tx, Ti, Tz components become zero, and the equation would look something like this. It would stay a simpler one. Unit meant you can decide what you want, limits of under simulation. So them which we discussed, that is simulations. What is not the entire simulation portfolio, but we are talking about the products simulation standard. So if I take there, we need to understand the material is linear, structure formations are small, and loads are static. That is no time dependent variation of the load. It is linear. That is, it be in a linear way, unlike say rubber or foam. Okay, we are not analyzing anything in the nonlinear domain. Point which I missed out, typical or what we are discussing now, that is all the kind of analysis. This static analysis has to be done only in cases where the expected deformations are small. Now, there are many theories on how do we decide whether deformation is small or more. Actually, in simple words, and reality as well, in terms of accuracy, the words that I use or tell everyone, if we can see the displacement by our eyes, then it needs a non-linear analysis. If it is not, then a linear static analysis should be good enough. Yeah, analyze, as I told you, it can stand infinite displacements and stresses. We do that, but just cautious that may not be getting the most accurate results. The only way we can get more accurate results is by using large deformation option, which is more a term of discussion, or we also use the option of with the sorry, we can directly jump onto the nonlinear analysis. That is the option that we have, and that means in one the limitation of simulation standard. So tell you that if it is an assembly with multiple parts, there is no point in using the parts with a. So if there are any conditions in a static analysis wherein there is a gap between two parts and they are expected to contact after the forces are applied, analysis is not eligible to be handled in static analysis or simulation standard. We need to have either dynamic or a nonlinear analysis to handle. In a static analysis, the matrix condition or the overall stiffness of the geometry is same throughout the analysis. So that differentiates the things, or that tells why we need what. Quickly navigate through the analysis process, but I believe most of you should be comfortable with this. But while I do that, do you have any questions on any of the topics that I have discussed as of now? Give it thought. Or I think we have almost covered 2 hours. Nothing wrong in giving a break. Again, we'll take a break for 5 minutes. I will in 5 minutes. Let's take a break. Of course, the chat window remains open. The session remains open. Please feel free to ask. let's start in. There are a few questions. Yeah, interesting question. There's again here. He wants saying, yeah, quality of meshing, or I don't know what exactly you meant, but definitely the meshing algorithm in Cedars plastics is far more stronger than what you might see in simulation. I would accept this point, but frankly, there are few or many limitations in that solver which I don't want to let here. Let it remain that it is a strong meshing. But at a broader level, a few things that we might want to understand. Number plastics algorithm is finite volume method. It is more of a CFD algorithm. I observed on the same lines, even the flow simulation algorithm is equally strong. So what we use in simulation is a structural, is a finite element method meshing, whereas that is done in plastics and flow simulation is more towards one more method called as finite volume method. So you can imagine the huge difference that is between these two algorithms. Then things like planar elements or plane stress, plane strain, not shell but the beam elements. Unfortunately, an algorithm like finite volume method can handle, and so those a kind of limitation. Uh, but interaction happens, etc. Obviously, there is enough in kind of integration between flow and plastics, and they do have many similarities in meshing and the quality of meshing. But if you are comparing the results, I don't see any reason why we can achieve the best quality of mesh in simulation and get equally high quality good results. As well, if I take the example of the newly added meshing algorithm, which has curvature based measure, it's been added in the last 3 years now, is a very sophisticated solver for meshing. It can handle any intricate geometries and it has its own different options. So I in the past few years, I don't remember any geometry which SolidWorks simulation could not mesh, and it is too huge and it is taking huge amount of time to mesh it, or it is basically some geometric problem and need to improve on the geometry. So not underestimate the simulation meshing solver. Of course, there are a few kind of features or options in plastics and flow which we would like to see in simulation. The simulation solver is a completely different algorithm and is meant for finite element analysis, not for anything else. That's a way to look at it. Question, guys? Please your patience for 1 more hour. You need to hear me for 1 more hour. I'll try to cover maximum amount of content that can be done in the time, but no, I'm open for any amount of questions. Flow of questions. Let me go back. So who have this, please try the simulation training manual. You is the old one with you in this with me, so that I can scroll through this while this training session is going on. Second, if you have not downloaded the files, again I missed out on showing that. Really, the SolidWorks trails are kept on the website on the public domain itself. It is not any logins or etc. It is directly open for anyone. So you can see here there is under simulation. You should be able to see it. So solid.com support training files. You should be able to see these things. Might want to have with you is these ones, SolidWorks simulation and simulation with results. Okay, so ensure you have these two with you, especially you to quickly see how we created, then the with results file set should be of use to you. Okay, let me open the files from the first lesson. Simulation with results. I'm opening the one with results. Okay, I open it. Um, most of you should be aware by now. We have a new different SolidWorks add-in toolbar by which you can either activate simulation or most of the products, and you can also select to activate it. Let me check question on the training PPT. I noticed that there is no update on some of it. Actually true, and as I mentioned, the training presentations are not updated for quite some time. They are as old as 2011. The word that I have from the training team is most of the content in terms of the content, it remains the same. So they are more used as a guide to teach, and they are not in one way or the other any obligation from the company to deliver it to the audience. Sticking to only these training manuals, we updated every year with their content. So know when the existing training will load from the front end or the VRC. So not download it. Please download it and keep it as a copy for yourself. Because the idea not be to support or give presentations in the long run, and we are going to many different things, like it could be online content or a different kind of concept. So after these training manuals will remain, which you can use as well as give it when you are when giving the software customer. But the presentations, obviously, we never give it to the customers. More used by me or TTs who are delivering the training or someone outside. So that it is. Let me start off with this lesson, wherein we'll more of see few front-end related stuff. So I believe this is it which we should be comfortable with. And secondly, if you are not aware, then unable to activate or deactivate any of the add-on products. Okay. In the book or in the PDF, you will see a few definitions. Even I do not remember these names, but this is what it is. There is command manager at the top. This top bar is called as the command manager. Most of you may not be aware that even simulation has got something as templates which can be used. I'll try to show it in one of the lessons or in due course of time. But if you want to use those templates frequently, then you can actually keep them over here active, and you can just drag and drop and use do analysis based on those templates. Simulation advisor. As a more scenario or a few initial meetings, this is a nice tool to be used. Do not miss out on that. So here there is something called a study advisor. It takes you through the different steps of analysis, and that especially for a new user to understand and follow the analysis. And also, the attractive thing in a demo wherein you are telling it is very easy. I just follow the advisor and I can do the analysis. There at the bottom, you will see the simulation studies or simulation tabs, and on the left, you are seeing the simulation study tree. So this tree should be of like other. These could be the words that I might be using during the training, and you be comfortable will help in grasp those words. So third, we can access the simulation content through tab over here, through different options that you can see in the graphics. You also have the feature tree. You can directly go through that and highlight any of the content, or you can do it through the feature tree. Okay, important thing which we should be aware of, because it is at the global level and should affect if you doing a few repetitive things, then this can make a difference. by the option was under simulation options. Okay, at this you will see something called as system options, and the second one is default options. So I want to select the right unit that I keep by default. Frankly, like many analysis software, we made handling of units very easy, especially while applying of forces, etc. The dialog box is a very context or a sensitive box wherein even if you enter the forces in a different unit, it can automatically convert. But it would be good to have this at the global level and activated in this way. So this one of it. Ensure you are selecting the right units which are free using, I would say. Visualization and colors of different things you can select from here. Nodes and fixtures, you can change the sizes of the symbols, the colors of different entities when they come on the software can be controlled. If you don't like certain color, you can change it. At the bottom you can see there are options by which you can decide whether you want to see the symbols where certain entity is created or you don't want to see it. There are also options over here, if you can see here. Check forward and fixture definition on duplicate faces. Slow on. So obviously when you're applying those loads, it is just ensuring you're not doing any duplication and checking it. Obviously, if this option is active, it is going to take more time on the front end to apply a load. As and when you apply the load, it is going to scroll through the analysis and do it. On a quick note, you have a dual screen. If the case, then please you can start off doing lesson number 1 when I'm explaining. You can hear to what I'm saying. You can also try these things on your own based on the training manual, and that should keep the pace for you. That should also help you get more doubts. When you do it yourself, I'm sure you'll find more doubts. Of course, try to follow what I'm doing. That can help in helping pace with me. Mesh. By default, we can select which kind of mesh to be used. Either it is a draft quality or a quality. The Jacobian points I did not discuss, but in a due course of time, it will definitely come. I'll discuss it in more detail. If not, also note it down over here. Measure settings. Again, these are the default settings. Deciding which measure, that is either the curvature-based measure or the standard measure, which of them you want to use by default, you are selecting over here. There is also an option called as remesh failed parts with incompatible mesh. So you select this. This is typically a meshing option. We'll see when we go more deep into meshing controls. But basically, it will try to mesh the geometry with a certain size of element. If it fails, then it can remesh the geometry with a more small element size. That can be done. Automate for non-composite shells. Other things, because most of these topics are not yet covered, so I'm not going deep. But these kind of controls are available over here. Result again first of all, solver, you can see here the default solver can be selected. You can leave it to automatic. I would suggest leave it to automatic so that software can decide which of the solvers to be used. So results folder, you are also deciding where the report should go, where the temporary database should go. By default, it will be at the location where you have the solid file. So the place where it is going. Then trend tracker. Topic has to be discussed, so nothing much we can see here now. Intermediate results, etc. This is fine. I can move on. Frankly, I think I'll not go through all of these. Please browse through them. Those are self-explanatory and should tell you the relevance of different options. These are more towards customizing the software, making things faster when you use it. And in the system on the general tab, typical in terms of errors, wrong messages, should you want to see them or you don't want to see them, how to show them, etc. is seen here. Loads and fixture symbol, how do you want them? Color for shell elements, it is actually giving us an option to select how will the bottom face color look like. So typically if it is orange, that means it is the bottom face, and other way around. And there's few other different options are there. I think I'll not go deep. Yeah, it's a useful thing. Ensure you are comfortable with this. This libraries. So by already having some things, we also link to the SolidWorks files options. But basically, if you are using any functions, etc., the where those are located is somewhere here. You can use it. The red curves are present here, or you can change it over here. Is relevant here? I think. Okay, let's start with this analysis. Let me check if any questions are there. What is it? Training PPT and okay. Will there be a separate training manual for simulation standard? Yeah, good question. Actually, A3 I covered this when I started this session. As of now, we do not have any intention of releasing a separate training manual because certain content is present in SolidWorks Premium. Even premium customers will need simulation, and you are giving the particular training manual. But so the status quo remains, wherein we have a solid simulation training manual, we have a SolidWorks motion training manual. Added that online, that is on DRC, you should be able to see a simulation standard oriented for analysis training PDF. So it can be downloaded. So typically for a simulation standard customer, we are giving simulation training manual, motion training manual, and the fatigue PDF which is present on the website. So also be aware that a few of the content which is covered in simulation training manual is actually not present in simulation standard. So you might want to list it and tell to the customer or prospect that these things need to be neglected. Then they are not present. If they want it, then it is only present in simulation professional. Guys, it's silence. Let me move on. Let's go. So I'm the study advisor. I am taking this option of new study. I start with a new study, and I can name it appropriately as want. Accepted. So I believe you all understand that we just follow this tree to do the analysis. Especially, I am required to apply the material. So I can select it from here, or I can also have a link to the materiality website where I get actually huge amount of material content available only for simulation customers. So I think it may not be relevant, but yes, you should be aware of this. Solution professional customers who are under subscription will get access to this particular content here. Then let me add some material to this and go ahead with it. I also want to fix the entry somewhere. So if I'm doing that, I'm getting these different options. One of them is fixed. Nowadays, it is very easy to understand. When I click on roller slider, I'm getting the video here showing if I select a particular option, how does it look on the software. I mean the picture actually work like. Just explanatory and should explain the concept in more detail. Yep. I select I'm option at the moment and I just apply. Oops. So that here every time I'm right clicking and I'm getting all the different options. There are external loads. I'm selecting a force. I select appropriate thing. Right. Okay, one important thing which I missed out. I believe most of you should be aware of this and or you should be knowing this. If you go material properties, you will see certain content in red color. If you see here, there is certain things in red. That's if I'm doing a linear static analysis, things like elastic modulus, Poisson's ratio, mass density, and yield strength are very important. Without them, the solution will not go ahead. When I'm doing a thermal analysis or a thermal expansion is expected, then I might need thermal expansion coefficient. If you are like tensile strength, etc., for different kind of analysis. So a bit of small color coding is done here to make understand what are the minimal material properties that are required for an analysis. Okay, that. And by the way, in the database, you will see certain material with the extension SS over here. There are few others which have something called as SN. Stress stand for stress strain curve. So the non-linear material properties of stress strain curve into them. There are also a few with SN which say that they have the SN curve or the number of cycles, the fatigue curve basically. So these two are of just a denomination to make you understand what is present inside the material library. But the things you have applied can be renamed. You can double click slowly over there and rename it and give it for your requirement. You can do it for any of these text. Okay. Now, when it comes to meshing, if you different parameters here, one of the things which we discuss is something called as a global size. And typically for tetrahedron, it is really difficult to imagine what this size could be. Is it one of the element or is it something different? So I think one of the images which is given in the training manual, if I scroll down to that image, let me go there. This one, it is on page 42. You can see here, this defines what it means. By the way, either a linear or a side, there is also H elements and H height, and this is what you are seeing here. So if you take this tetrahedron, and if this tetrahedron is put inside a sphere, the diameter of the sphere is nothing but the H value or the height of the element. So doing meshing, the location where we are, okay, here it is in the software, we are specifying the element size. This is a bit misleading, but this is nothing but the it encompasses within it. Based measure has a few more options, like it is talking about minimum number of elements in a circle. Okay, let me go back here. If I curvature based This is very easy. Standard measure, we have the option of tolerance. So if a size of 5 units, it is a default tolerance of 0.25. So it tries to create the elements. It is trying to create the elements anywhere between 4.75 to 5.25. So the elements are created only between this gap, and that is control that we have. And from an option called as automatic transition, this is nothing but this is helping this solver or telling the solver to create a refined mesh at dimensions are very small. Okay. The other hand, if I select the curvature based measure, again the same maximum element size comes, you minimum element size. Now this is a bit different in the sense, if I go to this element, let me check if this image can help me explain. Like if the PPT is any images on this, no, the press having no image. I have to get a image which I can use for explaining the curvature based mesh. Okay, I will not waste the time. I'll note this down. I'll ensure I show you with the image on this topic, curvature based mesh. By the way, I had in the webcast that I showed, I actually explained this topic in complete detail. That is, what relevance of these two parameters. Simply put, here talking of more of a again, if you imagine that sphere, it is kind of sphere that is present inside this geometry. We are talking of the maximum number of elements that want to fit inside this sphere, and we are also talking about the minimum number of elements. So assuming there is a sphere of say units, and we are talking about what is the size of the what is the maximum number of elements you want to ensure fit inside this element. And I think the best way I can explain it is using image. I try to find that image and try to explain it in the next session. And finally, this value is more of a transition. So when that happen, what can be done, can be understood over here. What default things that are created, I'm just accepting the media. Quick one, the draft quality option is somewhere here. If you remember, now we understood what is a draft quality and high quality. We can fit appropriately and use it. Automatic trials for solid, they can be fitted here. I believe you understood these two options. Just I'll discuss as and when the topic comes. I'll again an image for this. Yes, this is what it is. I just create the mesh. A mesh looks with different options or a few different things which you can actually let me check here. One of them is details. See here, this is telling us kind of mesh, the algorithm used, the different things, how many nodes are created. So in this job we have created around 19,000 nodes. There are 11,000 elements. The aspect ratio, that is the maximum aspect ratio, and other details are present. By the way, we'll be covering all these aspect ratio, etc. in due course. We also have this thing called as create mesh plot. Okay, so we are selecting mesh, aspect and Jacobian. So mesh, you are saying here, if you want, you can get an aspect ratio plot. It will give you the variation of aspect ratio on the geometry. Things which are present, of course, so clipping is present for that, etc. That goes as it is. I believe we are all set. We have held it, we have applied, and I'm going to solve at the moment. I'm selecting the default solver that it is taking. Okay, model with the results. Now, a few things on the results. Let's see. First of all, by default, it is rating these as per your global settings. You click on the results and select which result you want to see. You can quantities, that is, now you are comfortable with normal stresses, shear stresses. We also got principal stresses. There is something called a stress and intensity, which is the difference between the two extreme principal stresses. We have axial stresses. In terms of energy errors, we have this thing, or in terms of errors in the elements, we use two options of energy norm error and contact pressure error. Those is selected appropriately. This very handy front end wherein you can select anything and everything that you see on this processing or results. So it could be any of these results. It could be chart options, whether you see the minimum value on the screen, max values on the screen. All these can be selected here. Different things like how you want the results to be seen, whether discrete, continuous, or in the form of lines, etc. Whether see the model with the thing, or you also want to see the mesh with the results. All other things can be selected using this. I think this is an interesting option. I do most of you should ideally know it. If I take here is too low that I'm not able to see it. Yes, here it is. I expected. I was really using this option. Okay, let me try changing the transparency. Here it is. So here you can also see the original shape and the final shape of the geometry. So this is the option by which you can see actually how much displacement is happening. This is hugely exaggerated, but a good number of elements in this one. Okay, what else? I think there is some suggestion from one of you. You might want to use. Yes, I was looking for this image itself. We got it. This is present in help. Thank you, A3, for sharing this image. And I believe I'm able to see it when I'm zooming in. You can see a curvature-based measure. We are talking about maximum elements, minimum elements in the circle, and element growth ratio. So one is H value is the height of the element. No, I'm sorry, I cannot explain using this. I need an image wherein I'm actually seeing what is R, what is alpha, and H. Put it simply, as I told you, this is a circle. First of all, in terms of elements, minimum elements in this circle. That is, in this circle, I want to fit at least 10 elements. So say that, especially for curvature-based geometry, when I say that, it will ensure that the curvature is captured properly. On the end, what are the other two things that remains is the of the elements, that is the maximum size and the minimum size, that is limited. Those two are coming from these two values, that is the maximum element size, minimum element size, minimum number of elements to fit, and finally the growth ratio. So assuming it is to have a kind of mesh at a certain location, and when it is changing that size in the adjacent or within itself, within this circle, then the growth ratio allowed is maximum 1.5. So thank you, A3, for sharing this. I think I have a better image as well, but this looks excellent. Thank you. Let me go back to where I was in this thing. Okay, the results should be good. Okay, I think this is one thing which most of us are not comfortable or may not be aware. Is nodal values and element values. If you see here, okay. Let me know. Let me go to the image here. Where is it? Okay, if you see this, we take this particular image on the right side over here. There are 6 different elements. And each of these elements has a node and connected at the node. Well and good. But for calculations, the way it happens internally, we actually have something called as Gaussian points. If you see this text here, Gaussian points, those are present inside each element. So if you see nodes 1, 2, 3, 1, 2, etc., these are the nodes, are the points which are called as Gaussian points or Gauss points, what is seen here. These points are the locations where within a element the calculation happens. And typically when we are selecting say elemental values, okay, when we are selecting elemental values, the average of the results of 1 and 3 average of 3 Gaussian points within that particular element. On the other, if it is the nodal results, then it is the average of the Gaussian points which are all around the elements around this node. So first, does it explain you? Second, that when we are taking the nodal values, there are more averaged values across different elements or more number of elements, and that's the entire story. Did you understand the difference between nodal and elemental values? Let me just change here in the display. Nodal is by default, element is lesser. But by the way, one of the measures of seeing if the mesh quality is good is in these two options, that is nodal and elemental. If the mesh is good, then there will not be much difference between plots that you see for nodal and elemental value. It should be also. I'll show you assumption here. Let me check. Will be separated after an analysis. Is there any possibility that the volume of my element will change? I did not understand this question. After I run an analysis, is there any possibility that the volume of my element will change? Volume of your element will change, whether it is compressible. Yes, it will definitely change. By the way, typically, I'm not sure if you guys are aware of, the volumetric changes are defined by Poisson's ratio. So, okay, I think you're talking about the, I think you're talking about the intrinsic volume. Good. For Poisson's ratio is going to define a variation that is going to happen in the overall geometry. That is, say if I get a certain element and compress it in a certain direction, how much planar movement is going to be happening is going to be defined using Poisson's ratio. Again, I wish I had an image and I can explain it, but what it is. But take it for a local element, I would say you undergo huge amount of deformation, but I would not think that there would be any absolute change in volume. The volume would remain almost the same. I'm looking at situations like wherein I'm compressing this geometry in such a way that it has no place to change in the other two directions. Then obviously it has to create stresses and volumetric change. So frankly, if I had to put it in one word, answer is yes. There will be certain amount of volumetric changes, but they depend on the way the overall loading conditions. Yes, I think why can't the Poisson's ratio be higher than 4.9? It is always try to understand. Okay, the question is why can't the Poisson's ratio be higher than 4.9? Is it 0.9 or 0.5? 0.28. So what happens is, first we need to understand what is Poisson's ratio. Poisson's ratio is the ratio of lateral strain divided by um, strain that is happening in the axial direction. So if phi is an absolute condition, if I press the part in a certain direction, all volume will automatically move in the other two directions. Yeah, I think, yeah, this should be of use. Let me try to do something. Even X has an option to write and show you. Yes, annotation is there. Invite audio. Okay, I'll use the presentation. Right click. I'll use the white screen here. Okay. Let me take a pen. Pointer options pen. Okay. So one option for my very bad drawing. Okay. Let me. So assuming the Poisson's ratio is 0.5. Okay. This is very ideal condition. When I am applying a force like this, okay, the part will move in this direction, right? It will move in this direction. As it moves in this direction, the part expands somewhere. So assuming we are holding it over here, okay, I'm holding it here. The part needs to expand in these two directions. Okay. This is the ideal situation wherein I have unit in a certain direction and it is absolutely expanding in the other two directions, which is phi. Anything phi, it is not absolutely expanding, and this is where we are answering Thor's question. Yes, the volume would change if Poisson's ratio is below 0.5. On the if it is above 0.5, it becomes, this is a very if it is 0.6 or something, it becomes illogical situation. That is, I am putting this by, if for example this is not an absolute value, 5 units, I am expanding this by 6 units. This we see at the absolute ratios, then we should be able to understand why I am talking in this way. But this is the situation. So now for Thor's question, you can see, yes, there can be volumetric changes. For Dave's question, this explains why we cannot go below more than 0.5. 0.5 is a very ideal situation, especially for rubbers. Only rubbers, like rubber, shows behavior wherein if I press it, it will immediately expand in the other direction. It will not keep any, it will not absorb much forces. It change much. So guys, that explain you. As in this training, any other questions? Please hold for the last 10 to 15 minutes. We are almost at the end for today. But will stresses be 0 if the Poisson's ratio is 0.5? Ideally, yes, but stresses should come because you are holding it also at certain location. So if the part is free, it's not held anywhere, then we can expect Poisson's stresses to be 0. What described displacement in external forces and fixtures? So you can see here, good question. There is an option here called as displacement. So these options wherein I am holding it and saying this part is not moving at all. Okay. Second is where did prescribed displacement go? Okay, explain this option. When I have this option, I'm selecting a surface. Okay, I'm selecting a surface, and I can actually give a certain value of displacement, 2 millimeters. So I'm pushing this surface by 2 millimeters. Really, this is what is prescribed displacement. That's it. Any In terms of plots, frankly, I did not show you all the options, but I think you should explain them. In the sense, we also have something called a section clipping, and you can use compares. You can just run with these different options. Those should be, they are self-explanatory. Should tell you the different ways in which you can actually see the result. ISO plots in there. I think one of the useful utilities, especially when comparing with practical results, is the probe option. Nice option, especially you have practicals at a certain location. You can use it. It will create graphs, etc. Very good when we see the responses in dynamic also, but this is a very good tool. And just through the lesson to check if any other important topics are left in lesson 1. You can also do that. Ask me any questions or any that we have discussed in the last 3 hours. Is this particular process that we follow, but the most challenging part for you, and I wish you go a bit deep and do it and understand it, is this part when we are actually in these kind of comparisons. Okay, please do it. Use analysis, default analysis, fine analysis. See how the displacements and stresses vary. Those make a good understanding of how things can change when you are actually working on it. Second, comparison with analytical results. Very important. Very simple calculations. Please ensure we are comfortable with it. It also gives typically, instead of directly jumping onto some complex calculations for a customer's case, this is an example wherein you can get a good grip or understanding on how it all happens or how it can actually be correlated. All of you should be comfortable with this topic, and entire chapter, I want to ensure that you all have seen this page 65, understood, compared, and got the results accordingly. If you don't, please ask me. That is the best thing by which you can learn. Like that should give you some confidence or good confidence to FEA that you can get results which match as per your own manual calculation. And once that's there, then no big deal, you can handle any complex thing. Tip parts, I don't think there is nothing much to teach. You can explore. I would like to go into these questions. Let me check. I think I have a slide out of it. Yes, there is. Quickly have a feedback on these questions. The chat is open. Can you help me answer the first question? The processing stages of FEA include the following steps. Yes, those. Let me see how many participants are yet around. Good number. Excellent. Let's see how many of you are awake. I would like to have the answer for these questions. So what are pre-processing stages of net element analysis? Anyone? Yeah, answer this topic wherein I'm asking what are the pre-processing stages of a and Alex. So one input, definitely you need to know the material of the part. Yes, what else? Definitely, you need to know where all this part is going to be held. Fantastic. Conditions, when you want to load it. So A3 has finished it all. It says geometry, the CAD geometry, material, and physical working conditions. Put it simply, that is what it is. Conditions, yes. If it is an assembly, we need to understand the correct condition. Fantastic. I think it should be good enough. I can see there are at least 4 to 5 of you who are active in this training. I'm happy to see that. Next question. Density of finite element mesh dribble impact on the analysis. Very simple. What is it? Does it impact or does it have an impact? Obviously, let's go to the next question. Three on low definition. Fantastic, Alex. That should be useful. In general, we would favor finer, coarser mesh to obtain real analysis result. So, what do you favor? Being a coarse mesh or a fine mesh? The time required to solve the analysis will is, but this is an unavoidable consequence. Ideally, we will try to design optimum meshes showing reasonable accuracy levels and resulting in acceptable results. So, we will mesh that would ease time, right? This is avoidable consequence. Fantastic. I think you all have it. The primary unknown in finite element analysis is dash. This is a question, and most of us get it wrong. Is it displacement? Is it strain or stress? This is therefore the most accurate. Yeah, it. This is displacement. Who else stresses? Only one is remaining, which is strain. So, anyone strain? I have 2 stresses and 1 displacement. Stresses, Singapore is with displacement. Indonesia, Thailand says displacement. Right, this is a thing which we miss out, and actually the basic quantity or the first raw quantity that is available from finite element analysis is strain. You remember this. So what from the software, the first quantity will be strain. Then we actually find out the displacement or the total displacement. In itself, we can actually also find out the stresses. So stress by strain is Young's modulus. We know Young's modulus, they'll just multiply it and they'll get the stresses. Displacement is just the summation of the total strain. So this it is. So guys, my right, it is frankly when I was confused at many times in my life, but the reality, this is how FEA works. If you understood this, you will get a grasp of how it is going to work. Next question, the accurate. Okay, anybody wants to challenge me on this? Or you are off strain? Look, the accuracy levels of displacements, strains, and stresses. What are approximately the same, but David has given me some document from the help, which I'll look, but before that I'll finish these 2 questions. Are approximately the same, but significantly worse than that of dash complex. Therefore, to obtain good dash results, the mesh must be reasonably fine. I think you need it. It is the easy answer. Last button. the accuracy levels of I thought levels of stresses and strains are approximately the same, significantly worse than that of displacements. Okay. Therefore, to obtain good results, frankly, even I'm confused on this topic. I would on this question. I'll think on it once more or rephrase it in a better way so that we can discuss. But I accept what is mentioned here. But yeah, I would think more on this topic. The resultant solution approaching the analysis of the mathematical model. Okay, obviously refining. No big deal. Any questions? The primary unknown in FE is strains but not displacement. Yeah, good point. I think good. I am getting some challenges which I wanted. So David has shared a link with me and huge link. Okay. So, I'm not sure what should I see in this, but I'm a bit consuming document to read, but I'll go read once more. Okay, this is talking more on the sequence of the calculations. Okay, I got it. So I can put it in different ways. Actually, strain is the ratio of change in length. Okay, this change in length, if you try to understand the exact meanings of displacement. Now, for example, when you plot a displacement plot on software, what you're getting is the total displacement in the entire geometry. Am I right? It is not localized displacement in a certain element or anything. It is more of a summation, and this is more a derived quantity than that of the local elemental thing. And typically, that is, of course, these displacement values are available at different location inside the geometry as well. But remains, if I take it for that particular element, it is nothing but the change in length of that element compared to the original length, which is giving it the strain. And strains that are coming up in each seen in a 3D dimension, these summation of strains are actually leading to what as the summation or the total displacement of the entire geometry. Now, there are different ways of explaining it, but best way would be if I take a stiff matrix and the primary unknowns in that, even over there, if you see word is basically displacement itself. But displacement which we talk in the stiffness matrix is a little bit different than the displacement that we are showing it on the screen, which is called as the total displacement. To put different way, you might want to understand the difference between two words, which is called deformation and displacement. These bit funny and different words, they kind of differentiate themselves and they tell the difference. So is what the way I explained you this thing, or else in the next class I'll try to get a kind of stiffness matrix the way it is happening and try to explain it using that topic. but the link shared by David, which is from our online help, is more a generic topic than on it's basically talking of stresses and strains, etc., but not on FEM. So I'll have that matrix with me to explain it in more detail tomorrow. So thanks a lot for your patience today. Try to go through whatever content I had discussed today. Try to go through these exercises. Exercise on bracket. I think there is one more exercise down here. I'm comfortable with lesson 1, all these basics and all the topics that I discussed as of now. Catch up tomorrow morning 9 a.m. sharp. Try to be on time. And any questions, feel free to email me. Any options, any doubts, anything, feel free to email me. I can take it, either I can reply or I can discuss it in tomorrow's session. Okay. Thanks a lot for your time. Meet you tomorrow. Thank you.